Welcome everyone for this presentation. Today, Gero and I will be presenting on Turbomachinery simulations with CFturbo and CONVERGE. Um, so just a quick overview. First, Gero is going to go over introducing CFturbo. So he'll talk about all the design and modeling capabilities of CFturbo. Afterwards, I will talk about the new export option that is available in CFturbo, uh, using which we can directly import CFturbo files into Converge Studio and set up your CFD simulations. And finally, I'll talk about an end-to-end workflow where files exported from CFturbo will then, will create a case setup, create multiple case setups for different flow rates, and then finally generate a pump curve. So we'll be submitting the simulation on Converge Horizon, which is our cloud computing offering, and then get our pump performance curves. So Gero is now going to talk about CFturbo.
Okay, my part of the presentation is to give you an overview about the capabilities of the software CFturbo, and in addition explain our motivation for coupling our design system to CFD systems like Converge. Okay, CFturbo is a conceptual design system for turbomachinery. It can design impellers, stators, and volutes for the 5 main parts of turbomachinery: pumps, fans and blowers, compressors, and gas and hydro turbines. And the software supports the design of the 3 major types of impellers: the centrifugal type, the mixed flow, and the axial type. So despite the complexity of turbomachinery design, we have tried to make it as user-friendly as possible. We had to have an easy handling and transferring the design geometry to third-party systems. So there are in general, two different design options available in CFturbo. We can create new designs from scratch, or we can use a reverse engineering method to import existing geometries and use it as a start point for design modifications. So in general, for the new design from scratch, this is how CFturbo works. We are starting from a design point. That means we have to define a flow rate and a energy transmission as a pressure difference or a pump head, for instance, and the rotational speed. So these 3 numbers defining the design point. And in addition, we have to put in some fluid properties and inlet conditions. CFturbo then uses all the fundamental equations of the well-known turbomachinery design theory, like Bernoulli-Euler equation, the conservation equations, and so on. And in addition, a lot of empirical correlations that are available in books and papers. And all these empirical correlations are visible in CFturbo and can also be customized by the user if he has special knowledge in these fields. So, and then of course, there are a lot of geometry modeling capabilities in CFturbo to design all the different parts of such a complex machine. And at the end, we have a 3D model like here on the right side on the screen for the fluid and for the solid domains. And all the geometry is parametric in all details, and therefore CFturbo is ready to be used in batch mode or within optimization workflows. The next few slides illustrates the variety of designs that are possible in CFturbo for different machine types. The first slide here illustrates the pumps. So we see some different types here, the typical axial type of pump, then centrifugal pump with a volute, a mixed flow type here on the bottom left side, and on the bottom right side, this is a special type, a wastewater pump with very special requirements for very wide fluid areas. Most of our users are designing single-stage machines, but we also support multi-stage design, and this is an example of a three-stage pump. And these stages can be copies of each other. So that means we have only a master stage that we are designing, and the other stages are created automatically based on these data. All the stages can be independent, like it is required for compressible fluids in multi-stage compressors, for instance. Here are some examples for blowers and fans, starting with typical centrifugal blower, mixed flow type, then an automotive cooling fan here on the top right side. This is a very special blower, a squirrel cage blower, which is used for HVAC applications typically. And these are two contra-rotating axial impellers. So then we have the compressors, which have typically splitter blades for the radial or for the centrifugal type. This is an example of an axial compressor. And two examples, single stage and two-stage compressors with a volute on the outlet side. And then we have the gas turbines. Gas turbines are typically axial type, but of course also the radial inflow turbine is possible, which is typically used in turbochargers, for instance. And the last example slide here is handling the hydro turbines. We support both types, the centrifugal type, the so-called Francis turbine here on the top left side, and on the bottom side, an example of an axial type, a low head propeller turbine. Okay, and beside the new design from scratch, we can also use reverse engineering. That means we can import neutral CAD data from existing machines. This is an example of an centrifugal or mixed flow impeller. We can import step IHS per solid or VREP data, and the geometry have to be aligned to the internal coordinate system in CFturbo. And afterwards, you have simply select some surfaces for the blade and for the hub and for the shroud or the tip side, and then the geometry is created automatically, like here, visible on the right side. And it takes you a few minutes only, and afterwards you have the existing geometry in the CFturbo system, and it's parametric now, and you can make modifications or use it simply for automated CFD workflows. So the last slide here from this introduction is illustrating the design process in general. CFturbo is located at the beginning of this design process. So it's normally the starting point, the geometry handling. And then afterwards, you have two options to validate the design geometry. The first one is using meshing and simulation software like CONVERGE for validating the design geometry. The other option is using the 3D CAD interfaces in CFturbo, create prototypes and run experiments. In both cases, normally you have to step back to the design system based on the simulation results or measurement results. The reason is that the turbomachinery design is so complex that you need an iterative design approach to find the optimal solution. And these iterative loops can be done interactively based on the experience of the user, or it can be run automatically, and this is exactly the job of optimization software, that this loop is handled automatically. So in each case, for optimization, for interactive or automatic, a high quality CFD solver is very important in our design methodology. And that's exactly the reason that we start cooperation with a lot of CFD companies like Converge. So, and therefore we have started building a smooth interface to enable automated workflows with CFturbo and Converge. And this will be illustrated in the next slides.
All right. Thanks, Gero, for going over all the different kind of turbomachinery problems that CFturbo can solve, and also talk about the capabilities and talking about the design process that you follow. So now I'm gonna talk about the CFturbo export that's specifically for Converge. So right now, CFturbo has export functionality for different software, and Converge is now part of it. Now, in this export, there are two types of files that will be generated. The first is the STL files for all the different geometry component, right? The stator, impeller, volute, etc. So you'll have a separate STL file for each of those components, and then we have CFturbo-con file. So a file with this extension. It's an XML formatted file, and it contains all the simulation relevant information, such as what kind of project is it, whether it's pump, compressor, hydro turbine, gas turbine, etc. What are the fluid properties, and then it contains information about the geometry, the boundaries, and the boundary conditions. Also in CFturbo, you can set up your mesh settings as well as the solver settings for the safety simulation. So all of that is also written out in this CFturbo-con file. So now I'm going to take you over each of these options that are available to you. So the first is the geometry option, geometry export option. So here, first thing is you can define the domain type. So either you want the full flow domain or you want a virtual flow domain. So the difference is in the virtual flow domain, you exclude any kind of secondary flow paths. So for example, the flow paths between your impeller and the casing, right? During the initial design optimization, you don't want to worry about those secondary flow paths. So you will probably just do a virtual flow domain. So that's where you'll export it as a virtual flow domain. The periodicity, whether you want a full 360 geometry or you just want a periodic segment. So periodic segment will basically help you with your run times because you'll use less number of computational mesh. So you can use mixing plane models in Converge to simulate those periodic segments as well. And then finally, you have the surface triangulation. So we are generating STL files, so you can adjust the surface triangulation using this option. So you have three basic: coarse, medium, and fine. And then inside each, you can still customize it. You can set up your minimum and maximum element length to finalize your STL files that you're generating. Next, moving forward is the computational mesh settings that you can configure. So the very first thing is the base grid size, which is your Cartesian mesh base grid size, right? So you can specify any particular value. You have an option to also do grid scaling. So basically, you can start with a coarser mesh, and this is useful for a steady state simulation where we have seen if you start with a coarser mesh, you can get to convergence faster. So what we'll do is we'll get to steady state on a coarser grid, and once we have reached the steady state, we'll use that same field to run to continue with the final mesh. So you can start with one level coarser grids. You can also set up your boundary embeddings. So in these regions, impeller, stator, and volute regions, you have different boundaries. So you can set up what kind of refinement you need. So for example, here in the volute section, I am refining the diffuser and the splitter at embedding scale 2. So basically it tells you you'll have to set up the scale level, and then on the right you'll see what is the resulting grid size. So you can set up all your boundary embedding Similarly, you can also do the region embedding. So you can specify that you want the whole impeller to be embedded or the volute section to be embedded, etc. You also have the option to do velocity-based AMR. So in uh, certain regions, for example, in the impeller region, if you want to resolve the velocity gradients or define the areas based on the flow, you can activate the velocity-based AMR. So all you have to do is specify the scale for your velocity AMR. And finally, you have the refinement zones, which is basically cylindrical embedding. So if you want targeted mesh refinement in certain areas, you can define those refinement zones. And the last part on the CFturbo side is the solver settings. So for solver settings, you can set up different simulation types, right? You have the steady state simulation, you have the pseudo transient simulation, you have the transient simulation. And based on what kind of simulation type it is, you'll have different inputs for it. And similarly, you can also set up the numerical scheme. So for your momentum, turbulence, and all the other equations, you can set up your numerical schemes. So you have three options: central differencing, second order upwind, or first order upwind schemes. So this is all from the CFturbo side. So once you have configured everything and you export the files, now on the Converge side, what we have done is we have created a custom panel which can read those files that has been generated by CFturbo. And this custom panel is supported in Converge Studio version 5.1 and later. And in the future version, we'll just have a direct import option. Instead of using custom panel, you can just directly import the files like you normally do for other things. And basically, once you import the files here, you can generate an error-free convert CFD case right there. And then it's ready to be run either on cloud computing or locally or on your cluster. Also, if you want, if you don't want to use custom panels and you just want to do everything through command line, that is also available. So we have Converge Studio script, which is basically a JavaScript that can also read the CFturbo files and then generate your case setup. So now I'm just going to give you a quick demo of CFturbo export and then how we're importing those files in Converge CFD software. So this is your CFturbo interface. I'm just going to choose one of the sample projects that we have. It's a centrifugal pump case. Looks something like this. So I can just go and export it. So under the export options, you have all the different solvers, and then Converge is one of the options. So here we are just going to do a flow domain, full flow domain, full 360, and I'm just going to use, let's say, coarser export. For the mesh setting, let me change this to 5 millimeter, and I will run without the grid scaling. For the impeller part, I'll embed all the blade boundaries by level 2. So it will have 1.25 millimeter kind of grid size. And also let me refine my impeller region by level 1. So it will have you know 2.5 millimeter mesh. Um, I will not do any velocity AMR or anything in the volute, so I'll just turn off everything and no refinement zone. And for solver, I just want a steady state simulation, and I'm going to use second order upwind for all my numerical schemes. So that's all in the CFturbo part. I can go ahead and export these. So let me just select a folder where I want to export these files. And so this process would take maybe 10 seconds or something like that to generate these files. So now, see, it's just generating all these files. So you have the CFturbo conf file and all the STL files. So now I'll come to the convert side. So this is a custom panel where you have to just give the path to where your CFturbo conf file is. So I can just select this file and ask it to import. So it has imported the geometry, and then it has combined everything together and created all these interfaces between different parts. Then I can just select a folder uh, where I'm going to save this case. So let's see this case, and I can just export the case. So once I click export, it's going to export all the files there, and it's going to open a new project where it's going to import all those files that have just been exported. Here you can just check diagonals to make sure there is no geometry errors. So here there are no geometry errors. So this case is good to go, and we can actually go ahead and submit this case. All right. So yeah, it's basically as simple as that. A few clicks and you have a CFD case setup ready to be run. Now I'll take you through a workflow to generate the perm curves, right? So we generated one baseline setup. Now a perm curve is basically you'll have, let's say, head for different mass flow rates, etc. So what we have to do is we have to create multiple cases. So we have created this Python-based custom GUI which automates all this process. So the first part is case creation. So you can define what are mass flow rate you want to run that simulation for. It's going to create all those multiple mass flow rate cases based on the baseline setup. Once you have the setups, you can submit those cases on Converge Horizon. So you can select, which data location you want to run it at, or which hardware you want to use, and you can go ahead and submit it. All the cases will get submitted, and they can run on in parallel, basically, right? Once the cases have been submitted, you can do job monitoring. So look at whether they are running, are they pending, or if they have completed. If the cases have completed, then you can just simply post-process all the data. So what it will do is it will go to the cloud, download all the relevant data files, and post-process those data files to generate these pump curves. So it can generate data like head, torque, power required, efficiency, etc. Okay. So now I'll just show you a quick demo of the same. So here I have that GUI. So all I have to do is just select where my case is. So this is my case folder which I want to copy. Right. So I'll just select that, and then I'll just set up all the different uh, flow rates. This is all in kg per second. I can add these entries, and then I can create the cases. So it's going to create all a bunch of cases, right? So if I go to the folder, this was my baseline folder, and then it created a bunch of these other folders. Okay. Um, and then I can submit these cases. So I'll just go to the base folder where all those cases are right here. So it will show up what all Converge cases are available for submission. So I can just select, these four cases. I have to select some space where I want to run these cases, right? So just select something here, and the location or the destination at Horizon. So let me just create a new one, test demo, and then I submit these cases. Okay. So what it's going to do is it's going to upload all your files that you have, and as well as submit those cases one by one. So it has uploaded the first folder, and then it has submitted it now, and it's going to do that the same thing for all those four cases that we have just submitted. Yeah. So this is going to take maybe like a minute or so to submit all these cases. Right. Once these cases have been submitted, you can go to the monitoring case part. So this is submitting the last case now. Everything is completed. Now we can monitor. So I'll just select this. Basically, it's going to list out all the cases that are available that have been submitted on Horizon, and then you can monitor those selected cases. So it will show you, they have been set up for provisioning, and in few minutes they are going to start, and the cases are going to start on the cloud. And for post-processing, I already have run some cases, so I have some sample results. Let me choose that just to show you what the results look like. So I had already submitted these cases. These cases take around, the total wall time is around uh, 10 to 15 minutes. So I'll select all these cases and then just an output file where all the performance curve output is gonna uh, be sent. So and then post process the selected data. So it will create your pump curves, right? So I have head versus mass flow rate here. You can select what other quantities you want to look at, so power or efficiency, etc. Right? So yeah, so this is as simple as that. You can quickly submit cases and monitor those and load the data and create these pump curves pretty easily. Now talking about the cost and time benefits of doing all of this. So the simulation that I just ran, they have cell count of around 250,000, and it takes around 700 iterations to get converged result. On our 192 core machine, it takes 1 minute of runtime, right? So the runtime is only 1 minute, and we have submitted all these cases in parallel, right? So all the cases are submitted in parallel because we are submitting on Horizon where you can run on-demand cases. The total wall time per simulation is around 13 minutes, so it takes 10 to 12 minutes to provision a node on cloud computing, and once we get the node and we have necessary things over there, we run the simulation. So in total, it takes around 13 minutes of wall time. Now, the great thing is the cost efficiency. So to run these four simulation, or basically to run one design, it is costing around $6 on Horizon, right? So for evaluating one design, you're paying around $6, and the turnaround time from CFturbo, or basically from CAD to generating a pump curve, is around 15 minutes, right? So it took a minute to import the files. It took a minute to set up everything on the custom GUI that I just showed, and then in 30 minutes you will have all the results, right? So you have really quick turnaround time, and also your cost efficiency is also great. You only pay like $6 for one design. Now, if I extend it to a design optimization study, let's say if you are going to do a design optimization, generally what we do is we do a design of experiments where we'll run multiple design, where we'll vary the input parameters and generate multiple designs and evaluate those designs. So we have certain input and it will give certain output. Uh, and then what we do is, once we have that data, we use that data to train an ML emulator, which can reproduce similar results from certain input, and it will give certain output, and it will be trained on this DOE data. Once we have that ML emulator, that can run within seconds, less than a second, right? It can generate results for new input within a second. Then we run a global optimizer that uh, on that ML emulator, right? So we do, like, let's say, a genetic algorithm which is available through Converge. You can run a genetic algorithm optimizer on the ML emulator and get your optimized design, right? So let's say for DOE, you want to run 300 designs, right? So that will cost you around 1800 US dollars, and all those designs can be submitted in parallel. So there are like 1200 simulation, but on demand, a lot of hardware is available, so you can run multiple cases, and within few hours you will have all the results, right? It will take around an hour to do the AI/ML training and an hour to do an optimization study on this ML emulator and do some verification, right? So all of this process, basically your turnaround time could be within a day. You can do a whole optimization study, and the cost of that study is going to be around 1800 US dollar, right? So this is again an estimate. We have not tried it, so one of the next step is basically doing this design optimization study using CFturbo. So creating that whole workflow where everything would be very seamless, and you can do this optimization study pretty quickly. Okay. So yeah, that's pretty much it. Just to summarize, we showed a seamless export option from CFturbo, where CFturbo will generate certain files which can be directly read by Converge Studio, and you can have like a ready Turbomachinery CFD simulation with minimal user input. And we also took you through an efficient workflow where we demonstrated how you can generate pump performance curves, right? So from a single from CFturbo files, we created multiple case setups and ran that to generate all the pump curves. So all of that was done, and it was pretty fast, right? It took only 15 minutes to do all of it, to get from CAD to the results. It only took 15 minutes, and it only costed around $6, right? So now for the next steps, we are going to do a lot of studio enhancement, right? So a lot of things that I showed, for example, the custom panel, all of that functionality will be just part of a direct import option in Converge Studio. So instead of carrying around that custom panel, it will just be a direct import option in Studio. I think for the second point, the automated case creation, that's already part of Converge Studio, so that's already done, actually taken care of. The third point, the submitting Converge Horizon cases. So right now, Studio can submit single Horizon cases, but we are working on it and improving it such that you can submit multiple cases from Converge Studio on Horizon and also monitor those cases. So whatever I showed using my custom GUI, all of that. And then we'll also have built-in post-processing for Turbomachinery performance curves, right? For example, the pump curve that I showed, or let's say someone wants to run a speed line on a compressor simulation. So all of that we are trying to build into Converge Studio. So, you just get the data from relevant simulations, and then it will post-process all that data to generate all your performance curves. So yeah, that's it. Thank you all for your attention, and I'd like to thank Jero and his team at CFturbo for working with us on this, and working with them was pretty seamless, and also our studio team who helped in adding new APIs so that we can create that custom panel and import those geometries quite easily. So thank you everyone.